तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we had looked at the mixed formulation. We'll just quickly summarize what all we did in the last class so that we can follow the derivations further. We started with a series of definitions, and for example, we started with what is YAM, then what is ID, okay, and then we said that epsilon can be split into two parts, the volumetric part and the deviatoric part. Same way sigma can also be split, but one of the things which we emphasized is the fact that we are now going to look at not the irreducible form, that means displacement alone, but we said we'll look at both displacement, pressure and epsilon v as three of the variables that we will be interested in, okay, and hence we are stating sigma. I mean, this is a common thing what you know. The only thing is that we define delta sigma with that inverted hat to be one which you will get from delta epsilon through the constitutive equation. So this is the deviatoric part, that's the pressure part, okay, so that together will define as the sigma. So in other words, this is the fundamental definitions which all of you know, and then we wrote down the variational form. The variational form is very straightforward, and the first variational form is exactly the same as that of the virtual work form which you had encountered in the previous course. There is no difference between them, between this and what you had done before, and the only thing is that to that we add two more. If you really look at it closely, what essentially we are doing is that what happens or what should be 0, we are multiplying it by a weight function delta epsilon v and delta p. So these three are quite easy to understand, okay, and then we combine these three things, okay. So in other words, we have three equations. Note that we have now three equations, okay. We can combine them together to write Hugh-Vassilchev principle. In fact, you can come the other way as well. You can define the Hugh-Vassilchev functional, and from here, recognizing that we have displacement p and sigma, or rather sigma and epsilon v, you can rewrite that in terms of p and epsilon v as well, and then come down from Hugh-Vassilchev principle in the same fashion as you do for the irreducible form, for displacement form. Of course, this is written in terms of u sigma and epsilon. You can rewrite this in terms of p and epsilon v as well, and so from here you can come to this place, or from here you can go to the other side in a very similar fashion as we had done before. Okay, we will not worry about the Hugh-Vassilchev principle right now, but what we are interested in is here. It is much easier to understand from the formulation from this place, so we will start from here. We will come to Hugh-Vassilchev principle more in an elaborate fashion when we talk about the large deformation case. So in order to convert this into a finite element formulation, what we need is things which are again familiar to us, and these are the things that we need. And in other words, what we have done is to now define the continuum displacement in terms of the displacements of the nodes, and look at these two quantities. Now we have pressures as well, okay, defined in a very analogous fashion to that of displacement, okay, and then we have what are called as the shape functions for the pressure and the volumetric term as well, that is NP and NV. Both of them define these pressures which we had substituted, or which can be useful for us to substitute it back into the variational form. So having said that, having written these things, I can write epsilon and delta epsilon and sigma in terms which are familiar to us now, in terms of shape functions and the variations. Now variations defined with respect to the discretized form, okay, and our job is quite simple. Look at the logic, it's very simple. Having defined this, we'll go and plug these equations back into my variational forms, okay, and then write down a series or set of equations which I will use in order to solve for u, p and epsilon v. It may not be necessary for us to solve all these things together, and it may be at most instances possible to eliminate say p and epsilon v at an element level. Okay, we will see whether it is possible to do that. So as a first step, what I do is to substitute all the discretized form written in terms of shape functions into this mixed form and write down the corresponding equations, and let's see how they look like. Okay, I think we stopped at that point in the class, and if there are no questions we will progress further. Okay, let's see what happens to the first equation. I told you that you can yourself substitute it, you can see what happens. So first equation can be written, say, in terms of yum u double dot is equal to f. Okay, look at that equation and look at this. It's very obvious that the first term, which is the inertia term, goes as the m term. It's again a very familiar matrix, okay, M matrix, which is the mass matrix that you would have called in your earlier classes. So the mass matrix is, you substitute that, you can see that delta u transpose you can substitute in terms of n. So this is again n. So n transpose rho n transpose n is what is the mass matrix. Okay, so you can define that n d omega. Okay, you can, if you want, for further analysis you can either remove it or you can keep it as it is. Okay, for if you are going to do a static problem, then you can remove that particular term. If you are going to do a dynamic problem, then you can keep that straight away there. So next term is the p term, which is the internal force term. Remember that the internal force term comes from here, the second term here. Okay, remember that SU is replaced in terms of BU, so you will BU hat, you will get actually delta U transpose hat B transpose sigma. So B transpose sigma is what was coming into the picture as the internal forces. Remember that, that's what we used. So that is the second term that I have. So P is equal to integral B transpose sigma, okay, d omega. So that talks about our first equation. Now let us look at the second equation. Let me write this down. The second equation, what is the second equation? How do I get it? I substitute the discretized form into my second equation. Okay, look at these two terms, they are very easy to understand again. So you substitute for delta epsilon v and p from the previous case, and let me write this down as pp minus c, say p hat, is equal to 0. Can we repeat? M, yes, M is what? M I had already defined 1 1 1 0 0 0. I mean, just I had put M I had put here basically because it is easy to write it down. Yeah, mass, oh, this capital M, what is capital M? Capital M is nothing but a mass matrix. If I write it down as it is, it's consistent mass matrix, a very familiar term in the structural dynamics thing. So if you are, as I told you, if you are not interested, you can remove that and you will get back your original equation. So let us see what or how you get PP term. Okay, PP term comes from this first term. Okay, and what is that PP term will be. So delta epsilon v you are going to substitute from there. So obviously from this term here. Okay, and so substitute that and see how we can write down that term. Let's see what you get. PP, substitute it here. So let's see what you get. Simple integral omega delta epsilon v. So if I want to write, this is a number, but if you want to write it in a matrix notation, you can write it as transpose into this. Okay, in a matrix notation, because it's easier to follow matrix notation. So you can convert this and write this down in matrix notation. So you can write it down as delta epsilon v transpose the other terms there. So you can say that 1 by 3 I will keep that out, this 1 by 3 here I will keep that out. So delta epsilon v I am going to substitute in terms of NV. So NV transpose is my first term there. Then of course I have my M transpose term, then sigma term there, d omega, okay, is my first term PP. Then my second term comes from this term here, okay, again delta epsilon V transpose PP. My second term is what I call as C. So it's obvious that now, very simple, now I substitute this in terms of NP P hat, and this again the same way, delta epsilon V hat, okay, NV transpose. So together I get NV transpose NP d omega, P being taken outside, correct. So C is equal to omega into NV transpose NP d omega. I mean, this is what we did also in the last class. I hope things are clear. One of the points I want to state is that once you, it's so simple, finite element formulation is extremely simple. So once you have this kind of formulation, look at what we are doing, very, very mechanical. I defined discretized form, okay, till now, till this point, it is not finite element per se. Okay, Hughes issue principle comes into variational forms, they're not finite element. I enter finite element once I write these things. So once I know the physics, once I know the formulation, what I have to do is only take that out, substitute it into my variational form, okay. In fact, if you want, you can branch off from here, you can do some other technique, you can solve using some other technique as well. But once we are into finite element, we just substitute it into that expression. Is that clear? So we go to, yes, any questions?
Sir, in this PP that we have calculated from this equation, we put the value of delta EV transpose.
Delta epsilon V transpose, yes.
Delta epsilon V transpose.
Yeah.
But that is multiplying with 1 by 3 M transpose and sigma also.
Yes.
So, I mean, that will.
Okay, let me write that down clearly. If you have any doubts, we will. So you write this down so that this is a procedure. Okay, the doubt is how do I get this? Still not very clear. It is very simple. You see that I can write this down into delta V transpose NV transpose into 1/3 of M sigma minus P. Instead of P I am substituting it NP P hat, okay, d omega is equal to 0. Right, delta epsilon V transpose is that which belongs to the nodes, because actually I should put what we got it from discretization. So this is similar to delta U hat transpose that you would have had, okay, when we defined B transpose DBSK. So take that out. So I can write this down as delta epsilon V transpose omega integrating through omega NV transpose, so 1/3 M NV transpose NV transpose M NV transpose M sigma, right, d omega. That's my first term, okay, that because this delta V hat is the same for both the terms, minus the second term NV transpose NP into P hat, right. So the first term is what I call this as PP, because this being common, okay, this has to satisfy at every point. So this being common, okay, we can take that out. So PP minus C P hat, and C is what is the second term NV transpose NP P hat. Right, so that is what you get here in this term. Okay, so this is the, as I said, I deliberately did that because that's a standard way of writing that equation. Now let us come back to the third equation, okay, third equation is delta p. I think I'll just remove that and write that out again. Integral delta p into what is that we wrote? M transpose SU, M transpose SU, okay, minus epsilon v. Strictly speaking, that they should be the same and they should go to 0. Okay, so you can view it in a slightly crude fashion. We can say that this is 0, 0 multiplied by some quantity is equal to 0. You know, you can look at it, in order to understand it, you can look at it in that fashion as well. Right? So we're going to get three equations. I know the first equation, that's the first equation, and I know the second equation, and let's now develop the third equation. Okay, what is the third equation? Again, the procedure is exactly the same. Substitute for these quantities from the discretized quantity, and what do you get? Let us see what will you get as the first term. Delta p, again same way, delta p transpose I have to put. So let me call this as, you will see that I'll get C transpose out of it. Okay, C transpose, or minus in fact, epsilon, for the second term, epsilon hat V minus E U hat is equal to 0. This is the second term that you will get here from this term. Okay, it's very simple. Delta P, now I'm going to replace it with, so delta P hat, this will be replaced by transpose, so delta P hat transpose NP transpose. So if you look at the second term, let's look at the second term first. So I will get NP transpose NV, okay, NV into epsilon V hat, okay. So NP transpose NV d omega is nothing but C transpose, and so I get the first term to be minus C transpose epsilon V hat. Look at the second term. The second term is here, okay. Substitute in terms of SU, in terms of B, so that E will be, have a look at this term now, have a look at this term, okay, here, then you can write down E to be NP transpose, that's the first term that comes here, NP transpose, that NP transpose comes here, then M transpose, that's the M transpose comes here, then B, SU is written in terms of BU hat, okay, so NB, okay, d omega is what you will get as the three things. So you get that, that's the third equation, and that's the definition of E. Let me complete the picture by writing the second equation as well here, which we just removed. We'll write the second equation, PP minus C P hat is equal to 0. So that's the first equation, the second equation, this is the third equation. Remember what we wrote for C. C is N transpose, NV transpose, NP, right? D omega is what we wrote. So these are the three equations that we have, and we have to solve these three equations. Right. Now look at them. Let us see how we can solve them, solve these three equations. So because it is, oh, by the way, what is F? How do I get F? External forces, and that comes from this, obviously. I mean, though it's standard, we know that delta U transpose I substitute, so N transpose B, okay, then N transpose T d omega, right? So now you can solve this equation straight away. For example, look at that equation. It's so nice. It's very simple to solve them. So I can write P hat, okay, P hat to be, I can bring this guy to the other side. So I can write P hat in terms of C inverse PP, I can write P hat. And so the first thing I can do is to solve for straight away from these two equations without using the other guy. You can solve for this equation. Let's see how do I do that. So P hat, what is P hat from here? So C inverse PP. I mean, of course, they are matrix, just for clarity, I'm writing there. And epsilon V hat can be obtained from the second equation. Okay. Let's see, but there is going to be a small issue there, that is equal to C inverse, okay, E U hat, okay, C inverse E, so yeah, okay, C inverse transpose E U hat, okay, which can be slightly rewritten as, say, W U hat, where W is C inverse transpose E. When, of course, when NV is equal to NP, okay, which is the case most of the times we take, then C becomes C transpose. So this C inverse transpose can be written as C inverse. Is that clear? Yeah. No, there's a minus here. No, this should be plus here. First term, because the first term was a plus, so we get, right? That's a plus there, where W is that quantity. Is it clear? So now substituting for epsilon, okay, let us now do a small jugglery. Substituting for epsilon, I can write epsilon to be ID from the, look at this expression here, okay, I can write epsilon to be ID into BU hat. Look at what I'm going to do, it's very interesting. So plus 1/3, okay, M NV epsilon V hat. Right. Now for epsilon V hat, I'm going to substitute in terms of U hat, W U hat. So I can write this down as W into, sorry, U hat. Now look at this expression now. Does it strike anything? Does it? Look at that expression. This expression. Okay, what we have done is epsilon V we have written in terms of U hat, then resubstituted back into epsilon. Look at this expression here. Absolutely. So there is a relationship, looks like this relationship is very similar to my old relationship of B, right. Now the B is now, looks as if the B is now modified. The B looks like P has two terms in it. Okay, B has two terms in it, one term which is the dilatational terms and the other is the deviatoric term. Okay, so now B is split this, I mean it looks as if now B is split. Okay, now let me define NVW as say BV. Okay, BV, and write that down into in a matrix form, so that epsilon is now written as ID 1/3 M B and BV. Yes. BV, yes, of course, U hat is common to this, so I can write U hat ultimately. you can immediately foresee what I am going to get. Note that this is very similar to my splitting B into B deviatoric, B dilatational, okay, in our B bar method, okay, but we came through an entirely different route, a variational route, much more meaningful mathematically, okay, but still arrive at the same result, okay. So let us now proceed and see what would be my tangent stiffness matrix. You can foresee what we are going to get, okay. The procedure is again standard, there is no difference in the procedure. Let us see what we are going to do. What we are going to do is to take my first equation, as I said, let me remove this, okay, from further considerations. We have already considered these two guys here, okay. If you want to add, of course, the for the second term, that is mu double dot term, you can keep adding it. It is not going to change any of the things that I am going to do. You can keep adding it, but only thing I am going to do is to now take this B transpose sigma term, okay, and then see what we can do about it. That is equal to, remember what we wrote for sigma, id sigma hat, look at this term here, I am just keeping that there, please look at that term there, and then substitute that term here instead of the sigma, so that I will get B transpose, can you read that out, id sigma plus m np into p hat. But what is p hat? We just now derived what is p hat, C inverse pp. So I can write that down as C inverse pp. Okay, so I hope it's clear that the two terms id sigma, this inverted hat, m np C inverse pp, okay, d omega is what is my pp term. Now what I am going to do is to take this and then to a small jugglery, nothing else. If you want to do it, you can do it, or else you can, okay, do it in any other fashion you want, but just to make things easier to implement, we are going to go through this step, okay. I hope you are not lost out in what we are doing, okay. We are, the two equations we have taken, essentially I am able to, from the second equation I am able to get P, third equation I am able to eliminate epsilon V in favor of U hat, okay, resubstitute it back. So all my equations, ultimately when I solve it, okay, all my equations are in terms of nodal displacement only, but only thing is that the KT matrix what I am going to get is not my original B transpose DTB, but that is going to change, that is all, nothing else. So the second term, so there are two terms to this, let me write that down, omega B transpose id sigma hat plus B transpose m np C inverse pp d omega. So that would be the two terms. Now this term, the second term, I am going to rewrite it a bit differently, okay, because my, remember what is my pp, pp has an integral term in it, so I am going to write this down in a slightly different fashion, and I am going to write that as np d omega C inverse pp, okay, and then substitute for w from my previous expression, and then write this down as B transpose id, you can verify that what I am writing, just straightforward substitution, I do not have all the equations here, but you can verify that what you have, plus yeah, integral, I think 1/3 will come into picture because of my definition of W and so on. So W transpose NV transpose M transpose N M transpose, not P but sigma hat d omega. I'm substituting back all the equations which I know, which I derived, and so I'm going to write that down, something like that. Okay. Now, again, I'm doing some juggleries here, resubstituting it, all these expressions, so that I'll write this down as B transpose ID plus 1/3 BV transpose M sigma hat, or M transpose rather, M transpose sigma hat d omega is what I'll have. So this is what we actually arrived at as B transpose. So let me call this as my new B, okay, and so that I'll call this as, say, B bar, a new B which is B bar. Now the next step, this is P, so the next step is my calculation of KT. My calculation of KT would lead to my introducing dt here, omega B bar transpose, okay, this is rather B bar transpose, not B bar. So d sigma hat by d epsilon, okay, into d epsilon by du hat, which from here would again give rise to another B or B bar, so that I can write this down as B bar transpose, sorry, dt is t sigma hat by d epsilon, which is, or delta sigma hat by delta epsilon, that's what we introduced right in the beginning, into B bar into d omega. So this is, the step is standard, okay, again P is what, you remember this is what we did for the Newton-Raphson scheme, okay. So we, if you remember, we had B transpose sigma instead of this, and we defined this as B transpose d sigma by d epsilon into d epsilon by du, okay. Remember that we had this as dt, and remember that we had here B, so B transpose dtB is what we defined. In this case, it so happens that B is not there, we have a B bar, okay. B bar is the very thing that we had looked at, modified B in our earlier approach. So that is the KT now you are going to use to solve the equations, the Newton-Raphson scheme. Sometimes what people do is to combine these terms here into dt and define a new dt hat. There is nothing very different from what we are doing, okay, just dt is slightly rearranged, okay. So here you have, in this formulation, please note that there was a question on cross terms. In this formulation you have all the cross terms intact. It's a very rigorous formulation. In this formulation you will have all the cross terms intact, okay. So this whole thing is here, and then this would be written like this. So you will actually have 4 terms, all the cross terms, okay, which will go into the implementation of the finite element analysis. Now coming back to what we where we started from, we started with elastoplastic analysis, okay. What we have essentially done is to write down a small strain formulation for an incompressible or nearly incompressible material. That's what we had diversified, or we digressed from our elastoplastic analysis. We wrote down a small strain formulation, a mixed formulation for the analysis of nearly incompressible material, okay. And what I want to state is that now if you go and substitute at this dt your elastoplastic dt, then this formulation can be directly used for an elastoplastic analysis. If you are not interested in elastoplastic, but if you are interested in any other material still in the realm of small deformation, and if you are interested, that means that nu is equal to say 0.49, 495 and so on, okay, but the deformations are not very large, then you can use the same formulation, no difference, same formulation, but a corresponding dt can be used. This is what I wanted to tell you, that most of these algorithms are plug and play algorithms. It is not that I will repeat this if I have to do nonlinear elasticity, okay, the procedure is the same. So for solving a small deformation problem, this is the procedure, that is all. But I will add one more to this, what is it that I will add? I will add stress update algorithm if I have to solve plasticity problem, okay. Now the comment about this elements is that you should understand that most of the nonlinear analysis is done with not with higher order elements, okay. It is not usually recommended to do due to various reasons, theoretical reasons. Right now we are not in a position to see that, but usually most often we use only lower order elements. So for example, one of the elements which you may use here is say a quadrilateral element, okay, in which case you will define n in the same fashion as you had done for your earlier classes, but you would define np. Since np does not, dou np, look at this b, what enters here is only the gradient, that is dou nu, or the first differential of n is what appears there, but the first differential of p what we had defined, there is no corresponding p for np, there is no bp term, okay, that does not enter at that place. So we do not have problem of defining p, okay, in the same fashion as that of n. So usual method, usually what is done is that you will use and also note what is BV term. BV term is what we define here. This is the BV term. It is not, doesn't come from NV term. It comes from this BV term. So it's usual practice to define the U in this kind of element to be that at the nodes, and define P and epsilon V to be a constant inside an element. So in other words, it's a usual practice to distinguish between the degrees of freedom U and the other two degrees of freedom, and you please note that it is not all the time that you treat U, P and epsilon V to be as if they are degrees of freedom at the node. There are certain places where you will put degree of freedom at the node as well, P as a degree of freedom, but it's not the usual practice to define at the node degree of freedom U, P, epsilon V. It's a very important point, because that's where there's usually a confusion. It is not that here I have U, P and epsilon V. No, that is not what we are talking about. P and epsilon V are defined such that, say for example for this element, NP and NV are constants or unity. Okay, that is as of it is defined for this element, so it's discontinuous across the next element and so on. Same way you can extend this concept to a solid element as well. Is that clear? Now we will maybe later in the course we will define or re-derive equations for a tetrahedron elements. But what I want to again point out is that this is a general formulation and can be can be used, or information can be extracted from this to derive formulations or derive KT for plane stress or plane strain or axisymmetric, okay, and so on, 3D solid and so on. So the corresponding terms are now replaced when we go to say plane strain and axisymmetric. Of course, plane stress, there are certain issues. I may not have time to cover every element formulation, every element how it looks like. It may not be possible for us to cover in this course. The whole idea is to give you a background. Now if you, I recommend ZinQ Weeks volume 2. If you look at say Zinkiewicz volume 2, you will see how this particular element or this procedure is now used for deriving plane stress element. There are some changes, there are going to be some changes because of the way in which we operate for plane stress, but the procedure is the same. Okay, the concept behind it is the same. Okay, so we are not going to specialize everything because we have a lot more to cover, so that we are not going to do. But as an exercise, I would like you to have a look at the plane stress formulation in Zinkiewicz book. Okay, now having done that, we will get back to our elastoplastic analysis and close that part. Okay, before we go to the continuum mechanics aspects, let's now look at what are the things. We will motivate the cases now and then write down the equations and other things in the next class. So is it clear? This formulation is clear? Okay. Now we will now look at the stress update algorithm. So what we are going to do is to follow a very similar procedure as we did for one-dimensional case. Stress update algorithms are broadly classified into what are called as explicit algorithms. People call this as forward Euler method. Okay, sub-incrementation, explicit with sub-incrementation. We will define what is sub-incrementation as we go along. And then implicit algorithms. All of you by now intuitively know that all explicit schemes have conditional stability, or in other words, you can't have a large delta epsilon, then the algorithm is not stable. Okay, we know that intuitively because we know explicit finite element that is used in structural dynamics has some conditions attached to it called Courant condition. So same way here also you have some problems with explicit finite element or explicit rather scheme. So you may wonder why not we go to implicit scheme. There are very interesting things that would happen if the type of constitutive equations are different from that of Mises constitutive equation. So it's important that we understand explicit schemes, explicit with sub-integration or sub-incrementation rather, which is used extensively. Okay, and we will also look at in a broad sense what this implicit scheme as well. Now let's define what this, I've already done a lot of times I have stated what is explicit and what is implicit in this case. Okay, so as we go along we will see that as well. Now that is the say a part of the yield surface. My whole idea is that we are say at this point, remember where we are in the, that is the big loop, the incremental loop we are solving. We are inside the iteration loop. Okay, now I know how to form tangent stiffness matrix. Okay, now I know how to solve for u. I know or I have to learn only how to do stress update. So we are right here, stress update, we are going out and looking at the issues that are involved in stress update, right. So at the end of this you will know all aspects of small deformation elastoplastic analysis. We'll complete the whole show there, and on the way you also learned how to do small deformation elastic analysis also. Though it has not much meaning to it, there are Puritans will not agree with you when you say I am going to do small deformation elastic analysis with the, or in other words if I say that I will do using Hooke's law, I will make nu is equal to 0.49 and do certain analysis, people may not agree with you, but for many practical problems, okay, this will be a good approach where nu is equal to 0.45 or 0.49 rather, you can use this formulation. So let's quickly look at what we mean by the stress update algorithm. So the issues are very similar to what we did in the previous class. So what I have to do is to now take this point, the stress point, which is say inside the yield curve or the yield surface, which means that we are in the elastic region to the plastic region. Okay. So I may have to go from this point to this point, and as I move from these 2 points, what I also have to do is to update the yield surface. So 2 things I am doing. One is to update my stress as well as update the yield surface. So what is the issue? As I update the stress and as I update the yield surface, it should be in such a fashion that ultimately I will lie on the updated yield surface. That is the issue. So that's the only thing that poses a lot of problems. Now I will state in a nutshell what we are going to do and then expand this in the next class. Okay. I am going to follow our elastic predictor plastic corrector approach. So from here I am going to predict, okay, in an elastic fashion. Okay, I am going to go out of the yield surface and reach a point which I will call as sigma elastic. Okay. Obviously you are going to pounce on me, he is going to say that it is not going to lie outside the yield surface. Yes, I know that. Then I will correct it, I will come back and lie, okay, on I will come back to a point which is corrected point, okay, which I will call as sigma t. As I correct it and come back, okay, I will also update the yield surface by calculating epsilon p or delta epsilon p. So from here my yield surface will go out. So that will be my new yield surface. So when I do that explicitly, I will find that obviously I may not lie on the yield surface. Okay. Then I will correct this trial sigma by pulling it back in a simple fashion to the yield surface, the updated yield surface, and I will get what is called as the sigma corrected. Now in order to do this, I realize that I need one important factor. What is it? That R, which I did in the one dimensional case. Okay. How did I calculate R? I know where I hit the yield point. Okay. In the same fashion, I have to now find out, as I move from this point to this point, where I will contact the yield surface. Okay. That point I need to know. So that point is called as the sigma, say, contact. That point where I contact the yield surface is called sigma c. Note again, the concept is very similar. So this is what I need not correct, okay, and this is the part, that's the part which I have to correct. Right? Okay. So how am I going to do that, and how am I going to ultimately calculate sigma CR by means of an explicit scheme is what will be the focus of next lecture. So we will stop here. Is there any questions? We will stop here and we will continue in the next class.